Hi, I'm Dave Kassler, amateur radio call sign KE0OG, the author of the Ask Dave column in QST, and this is the monthly video supplement to that column. The column in particular for October 2022 is this one right here. And the last article in it has to do with noise floor and noise figure. And I thought what I'd do is go into a little bit more detail about thermal noise, because it's a kind of noise that's not very well understood by many amateurs. So let's take a look at some charts. Thermal noise is only one type of radio noise, and for most HF operators is not an issue at all. There are a number of types of radio noise, and I suppose you could probably add more favorite types of noise to this. There is noise generated by man-made machines, such as grow lights for plants, motors like air conditioning equipment and so on, even your refrigerator. And this usually is fairly short range. You get a little ways away from it and you don't have much. But if you're in the city, you might have a lot of this. Also, there are harmonics and intermod from other radio equipment, not to mention hams accidentally interfering with each other. There's also noise generated by atmospheric effects. Many of you may have seen a video on television of Hurricane Ian as it approached the coast of Florida. And you could see lots and lots of lightning going on. There is anywhere in the world some lightning somewhere, and lightning strikes generate a lot of RF energy, which is spread by the ionosphere. There's also aurora, things like that create noise. There is galactic noise, in our case mostly from the sun. I remember when I worked at 660th Radar Squadron in the Air Force, in order to calibrate our antenna, we would point it at the sun. We'd wiggle it around to where we got the most noise, and the sun is quite a good radar noise source. And then we would tweak the antenna pointing algorithm so that it knew it was pointing at the sun, because we always knew where the sun was. Now, this galactic noise, which comes from a variety of things, to radio astronomers, what to us is noise is in fact their data. And they use it for many, many different purposes. Interestingly, one of the people who has been looking at galactic noise is Joe Taylor, a ham and a Nobel laureate, who has worked with quasars and other things going on in the heavens, and some of the great advances in our ability to communicate over ham radios, such as FT8, come from Joe Taylor and K1JT. And in fact, it is the result of his work trying to tease information out of the galactic noise that has led to these phenomenal communications characteristics that we have now, like FT8 and so on. Now, the last one is called thermal noise, and this is the one I'm going to focus on here. It is noise generated by everything, thermal noise. This is where this video focuses. Thermal noise is generated by matter at any temperature above absolute zero, which means anything, because nothing is at absolute zero. One of the reasons I want to focus on this is because by the time you get up to around 15 meters, and certainly into 10 meters and 6 meters, you will find that all these other types of noise fade away, except your harmonics and intermod from other radio equipment. But in the background, there will be thermal noise. It sort of sets a noise floor on everything, and it's that I wanted to talk about. But before we do, let's take a look at what I call the magic of radio. The magic of radio is that if you have a 100-watt transmitter, that's 50 dBm of power going out to your antenna. I'm assuming you've got a 1-to-1 SWR and a dipole. The person on the other end is receiving an S5 signal. The S5 signal is minus 97 dBm. That's decibels related to a milliwatt. The difference between the two is 147 dBm, or approximately 1 out of 147 trillion out of the original 100 watts that makes it to the receiver input. The amount of path loss is just incredible. It's a trillion, over a trillion. The rest of the signal is lost. It goes elsewhere, perhaps to be heard by other people. Perhaps it helps heat up the trees around you, or it goes into outer space. But the fact is that the amount of signal that makes it to your radio is one very, very, very tiny percent of the signal that is transmitted. We can do this by looking at an equivalent in money. The U.S. federal budget is approximately $6 trillion every year. Okay, that's, or 6 times 10 to the 12th, 12 zeros. Now, if you were to take all the money in the federal budget and create the money equivalent of an isotropic antenna and throw that money in every direction, we want to see how much is captured by our so-called money radio. Well, 6 trillion multiplied by the path loss here, 1.47 times 10 to the minus 14, is 9 cents. So if a 100-watt signal is equated to the national budget worth of radio signal, an S5 signal at the receiver, and by the way, that's a perfectly good signal, is 9 cents. So here's the bottom line. Almost all of the radio energy sent from a transmitter never gets to the receiver. It's 99, well, there's 14 nines there, okay. So that's how much signal is lost. Wouldn't it be nice if we could just send the amount directly to a person? But of course we don't know who's going to hear us and answer our CQ. So what I want to look at is dealing with this, since while we think of 100 watts as a relatively strong signal, the fact is that there is so much path loss that what comes to us is very small. And we still have to get through all that radio noise. Now, I want to look at thermal noise, so I turned to the 2021 ARRL Handbook. It's the 98th edition. And looked up thermal noise in section 5. So why do we care about thermal noise? The answer is that at most HF frequencies up to about 15 meters, we don't, because other sources of noise are much stronger. And so the thermal noise sort of fades into the background. We don't even hear it. Now, but above this frequency, we do start to care because thermal noise becomes dominant. Now, if you look at a lump of matter in front of you, say a peanut, it doesn't seem to be generating any noise, but if you were to, use your ohmmeter to check it out, you'd find nothing there. Although if you use a potato, it actually generates a little electricity, but certainly not RF. The thing is that even if a signal is below S1, we have the capability to amplify that signal gazillions of times. In this case, of the example I gave, 1 trillion times, unless somewhere in there noise interferes. Now, what happens at VHF and UHF is that thermal noise becomes the limiting factor in amplification. And thermal noise may be extremely small, but remember, if you're taking the original signal and cutting it by 1 trillion, there's not much signal there, and thermal noise can actually become the limiting factor in amplification. Where does thermal noise come from? Well, it comes from everything. An electric current is defined as a flow of charged particles. Now, we usually talk about electrons, but it can be other charged particles. Like in salt water, we have the chlorine ions and the sodium ions separate from each other. They've got opposite charge, and they can flow in different directions, depending on where the electric current is flowing. But usually we talk about electrons. Temperature, as we commonly know it, is a measure of the amount of molecular and atomic movement. The hotter the material, the more it moves. So things don't hold still. If something is warm, it's going to be wiggling more. If it's in a gas, the gas particles will hit each other more and the pressure will go up. Now, the corollary to this is that there is a temperature at which nothing moves. This is called absolute zero, or 0 Kelvin. The Kelvin scale starts at whatever absolute zero is. It has been measured at about minus 273.15 degrees centigrade, or 459.67 degrees Fahrenheit. Note that with Kelvin we do not use degrees, it's just Kelvin. But with centigrade and Fahrenheit we can use degrees. Now, the absolute zero is not achievable in practice. You can't do it because there's going to be some movement because there is so-called quantum noise. But it is, scientists have come very close, within fractions of a degree of absolute zero. So the background temperature of the universe, by the way, the whole universe, varies in which direction you look, but it's about 3 Kelvin. So in other words, minus 270 degrees centigrade. Now, we might say, well, 3 Kelvin, that is some energy. Yes, it is, but it's almost vanishingly small. So everything as it moves. Now, this is the great conceptual leap. As electrons move, by definition, that's an electric current. It's a flow of electrons. Electrons move, that's an electric current. And what happens if that current it continues in there? That means each atom emanates a very tiny amount of radio waves by just sitting there. And by tiny, I mean tiny, tiny, tiny amount of electricity by sitting there. But when we are working with VHF and UHF, and we want to do unusual, what are called weak signal work, we are very interested in this thermal noise because it turns out that the signal is at about the same as the amount of noise made by thermal noise. And the other problem is that anything in an amplifier, all amplifiers are made of real matter. And so therefore the amplifier itself can add noise. And if it adds enough noise, it will obliterate the signal we are looking for. So here is a signal that, say, that might be 10 dB above the background noise. But if we have a radio that adds 10 dB of noise in our first amplifier, which is the most important here, it can obliterate that signal. So we like to do something about it. It's extremely important in radar and in radio astronomy. Also, if you're trying to do moon bounce, meteor bounce, and so on, the signals that are reflected are very tiny. So just how much? Can we quantify how much thermal noise there is? The answer is, of course, yes. Otherwise, I wouldn't have this slide. The voltage of the noise, this is the field voltage in the electromagnetic field, okay? This is what would be picked up by an antenna and so on, is the square root of this quantity, 4 times K times TRB. Now, Boltzmann's constant is K, and this is a constant of the universe, and it is approximately 1.38 times 10 to the minus 23 joules per Kelvin. A joule is a measure of power, and Kelvin, of course, is our measure of degrees. So T is the temperature in Kelvin. R is the resistance of the matter that we happen to be using, and B is the bandwidth in hertz. Now, if we convert this voltage to power, remember power equals the current times the voltage, turns out the resistance value drops out. we get the power, the noise power, is K, Boltzmann's constant, times the temperature in Kelvin, times B, which is the bandwidth in hertz. Okay? Note that the resistance drops out. So the noise power is independent of the resistance. It just has to do with the device. And since K is a constant, it's affected by the temperature and the bandwidth. Now, thermal noise is modeled as frequency independent. In other words, it's the same at every frequency. It's just noise. With the magnitude at any given time modeled as additive white Gaussian noise. So this means that the volume, the voltage, the power of the noise fits in terms of the amount of power, a bell curve, a normal bell curve. In other words, it can be anything from 0 to infinity, but it could actually from minus infinity to plus infinity, but that's extremely rare. So we are looking at noise that is, maybe 4 sigma away from the norm. Will cover 99.9% of the noise, and you'll be fine. Okay, let's see how bandwidth affects the noise. I set up my signal generator to create noise. There is actually a setting on my signal generator to create noise, and here it is. And it goes from 0 hertz all the way up to 1.5 gigahertz. It's the same volume of noise. Now, my spectrum analyzer tends to tweak things a little bit here. Pretend that's a level number. It's the same at any frequency if we're talking thermal noise. Now, a narrow bandwidth captures less noise because it just captures this noise power. And remember, it's additive white Gaussian noise. So if you take some Gaussian noise at certain frequencies and some additive white Gaussian noise at another frequency, you just add them up. So if you have a wider bandwidth, you pull in more noise. So that gets us back to this equation here, where we are dealing with the temperature and the bandwidth, and then just Boltzmann's constant. So let's get real and take a look at an actual example. Standard temperature is about 290 degrees Kelvin, which is about 62 degrees Fahrenheit. Now, if you say, that's not very warm, well, the original work that did this sort of thing was done in England and the northern part of Europe, and a very nice summer day might be 62 degrees Fahrenheit. So the noise power can be at room temperature, which is the standard temperature, 400 times 10 to the minus 23rd. That's 400, it's 1 over 400 with 23 zeros. And B is the bandwidth in hertz. For example, a single sideband signal is approximately 2.5 kilohertz wide. So noise power in this bandwidth is 2.5 times 10 to the third times 400 times 10 to the minus 23 equals 1,000 times 10 to the minus 20, or 1 times 10 to the minus 17 watts, or 1 times 10 to the minus 14th milliwatts, or about minus 140 dBm. So if you've got a bandwidth of 2.5 kilohertz, no matter where you tune in VHF, UHF, microwave, and so on, this is the noise environment that you are in. Now, this is the over-the-air noise atop our single sideband signal. So how much signal do we need? For a single sideband signal to be well understood, it should have a signal-to-noise ratio of at least 10 dB. So if we receive a minus 130 dBm signal, which is 10 times, 10 dB is a factor of 10, we would like to be able to receive it. After all, we can amplify by 1 trillion times or so, right? Well, it depends on whether the first stage of the amplifier, which is the most important stage, When you amplify a signal, by even just several hundred times, it turns out that the noise kind of fades away at that point. All amplifier stages add noise because they're thermal noise. But by this time, the signal is so big, the additional thermal noise makes very, very little difference. Now, amplifiers are made of real components, which are matter, and the amplifier will add noise. The noise is actually generated inside the amplifier. The amount of noise added is called the amplifier's noise figure when using decibels. Let's take an example. My Ten-Tech Jupiter boasts a noise figure of 11 dB. Now, I actually measured it, did a test setup to measure it, was 13 dB. For HF, that's fine, because band noise is so high that thermal noise doesn't come into play. But if we're trying to receive our sample single sideband signal and the input amp adds 11 dB of noise, our signal fades down to -1 dB or 1 dB in the noise. In other words, we no longer have this nice 10 dB signal to noise ratio. We have it down in the noise. It's lost in the noise. Okay? So let's look at some diagrams from section 5 of the ARRL handbook. This is how noise figure works. We have an external noise source. This is our -140 dBm. And then here is a resistor to represent the amplifier's added noise, and then a noiseless amplifier out here. We will find that this is gain, right here, the gain of the amplifier. The output noise will be the gain times the sum of the two temperatures, of course, times Boltzmann's constant, okay? So an amplifier has noise. We call that the noise figure when we do it in logarithms, okay? Let's take an example of that. Here's a low noise preamp put in front of a receiver. This is a rather poor receiver. It has a noise figure of 20 dB, which is 100. Now, there's two ways you can look at this. One, you can add the 20 dB to the signal and work in decibels, or you can multiply the noise by 100 and just work in ratios. It's far easier to work in decibels. In other words, we could say that this is a noise-free amplifier to which is added 20 dB of noise. Okay, so a signal here going in will come out with the signal-to-noise ratio reduced by 20 dB, or a factor of 100, because of the added noise. Now, if this is fed a strong signal, the added noise won't matter very much. So if this is a strong signal, we take a low-noise RF amplifier that's designed for low noise, like a parametric amplifier, and it's got a noise figure of 3 dB, or in other words, multiplying by 2, okay? And the gain is 15 dB, or 31.6 times, okay? So you've got your receiver input from the antenna, and you've got to take, the different noise figures into account, and we get a gain of 5.13. That's a multiplicative gain. So the noise figure here is 7.1 dB, okay, because it's got a noise figure of 3. So that's the amplifier itself. And we've taken our original input here, okay, and come up with this. The system has a noise figure of 7.1. So that means that this system, by simply adding a low noise preamp, will cause the noise figure of the whole system to drop from 20 dB to 7.1 dB. That's 13 dB difference. That's 2 times 10 or 20. 20, a factor of 20 reduction in the noise, and the signal stays the same going through. This is why in your HF receiver, modern HF receivers have what are called preamps. Now, preamps are going to add noise, okay? But if the preamp is made right, it's a very low noise preamp, and it can actually help you separate the signal from the noise. But this works best with thermal noise, and that means that you're at, like 15 meters or 10 meters or 6 meters or something like that. Now, I want to show you one more thing that you can do. Here is a system. Got an antenna, a piece of coax, a low noise amplifier, and a receiver. And we come up with a noise figure of 1.07 dB right here, okay? And the total noise figure is 2.57, okay? Now, up here, we move the RF amplifier in front of the coax because the coax actually creates noise and adds it to here, okay? And we find that by moving the preamp to the antenna, we get a lower noise figure, okay? That means less noise. We can hear more because the noise has gone down. This is important at like 15 and 10 and 6 meters. It's vitally important when you're getting up to weak signal work in the VHF, UHF, and microwave region. This is why your satellite antenna has an LNA, a low noise amplifier, that's actually in the dish, right at the feed horn, that gets the signal big enough so that it can go through the coax without getting a bunch more noise on it. You get a low noise figure with it. This is the way to go. By the way, if you look at HF receive-only antennas that are loops, like a 3-foot loop, they have a preamp right at the input from the loop itself, so that the signal will be multiplied enough that there'll be something to hear by the time you get down to the receiver. And that's why they have preamps in them. Okay, that's why if you're doing moon bounce and so on, you want to move your preamp out to the antenna itself. Now, how can we reduce thermal noise? Well, we note again that it's a function of Boltzmann's constant, which is a constant of the universe. We can't change it. But it's the temperature and the bandwidth that do it. One thing we can do, instead of using our normal circuits, use special circuits that are known to add less noise, such as parametric amplifiers and stuff, and put them right at the antenna. Or you can lower the temperature of the preamp. If you're in radio astronomy, your preamp is probably cooled several hundred degrees below 0 centigrade or Celsius. This can be done with liquid hydrogen or liquid helium, and these are used in radio astronomy so that we have very, very weak signals coming from the galaxy. We just can't afford to add any more noise to that. So we're looking at noise figures of like 0.1 or 0.2 dB that add almost no noise. Another thing you can do is reduce the bandwidth to just that necessary for communications. So if you're receiving CW, go to a lower bandwidth. Try this out on your HF receiver. If you can vary the bandwidth, tune in a CW signal, and then lower the bandwidth to where it just covers the signal. You'll find there's a lot less noise. Also, you can use special coding techniques that provide a coding gain. And this is what is happening in radio astronomy. And Joe Taylor, who's a ham, has taken some of these techniques and is creating modes. It started out with JT65 that became popular. It started out as a moon bounce algorithm and made its way to HF. It's not optimized for HF. So he came out with JT9, which was more optimized for HF, but everybody was on JT65. And then he and a friend came out with FT8. and FT8 has swept HF because the signaling go-around time is a half a minute instead of 2 minutes. Okay, so in the end, we've learned about noise, thermal noise, how we can reduce it by reconfiguring our system to put the preamp out at the antenna, using special circuits in the preamp to reduce the noise, if we're going to do like moonbouts or something like that. When you get into liquid cooling, you're getting exotic, okay? And there's a lot of expense involved with cooling that preamp. But here's the challenge I present to you. This is the Shannon-Hartley theorem on channel capacity. The challenge is this right here represents the maximum achievable bit rate in a system with a given bandwidth and a given signal-to-noise ratio. This is the maximum achievable, and it's through an analog communications channel subject to additive white Gaussian noise of noise power n, and then our signal has some relationship to that. Okay, C is the channel capacity in bits per second, a theoretical upper bound on the net bit rate. By the way, the net bit rate is the information rate, not the information rate plus the parity bits. It's the information rate, meaning if you send faster and add more parity bits, you actually can get more channel capacity, okay? Now, the challenge here is this is not a completely solved problem. In the last 40 or 50 years, since I've been alive, there has been enormous improvement, but there is still room to go. And you can help participate in this by understanding the algorithms used for FT8, JT65, there's other new modes for moon bounce and so on, to see how this is done. So, there you go. I hope you enjoyed this little explanation of noise, and I hope I've piqued your interest. If I have, I encourage you to go to section 5.8 of the ARRL handbook, or wherever it may have moved in the latest one. Read the chapter on noise. It goes into far more detail. By the way, entire graduate courses are taught on this subject, and some people devote their life to it, trying to reduce noise. Reducing noise on regular circuits gave us the internet. It came because we had this kind of information theory that showed us how to send data over noisy lines to get data through it with any degree of accuracy that we want, depending on how it's coded. But the bottom line is this kind of information theory allows us to do amazing things with amazing amount of bits. Now, no technique will give you 0 errors, but you can come arbitrarily close depending on how you set things up. So there you have it. If you have not yet joined the ARRL, I encourage you to do so. And until we next meet, 73.